Hello everyone. For this tutorial video, I like to talk about how to solve linear equations, which are equations that give lines when graphed out for specific values of x. A linear equation is said to be in conventional or standard form if it is in a times x plus b equals 0. It should follow that if we have it in a form like this, to solve x for itself, we would do the order of operations, or PEMDAS, in reverse, which you may remember from arithmetic and pre-algebra classes. So, for example, since we know multiplication generally comes first, when you do it in reverse, addition and subtraction comes first instead. So that way, you isolate x and its coefficients on one side. So we would subtract b from both sides. And lastly, to get x all by itself with no coefficients, we would simply divide both sides by the coefficient a. We conclude that x is exactly equal to negative b over a, given that the linear equation is in standard form. But in many cases, we will have to simplify our expression or equation first, before we can get it in the form ax plus b equals 0. For example, if we are given this, it looks messy at first and nothing like a linear equation, but we can simplify it by distributing everything in the parentheses and then adding and subtracting like terms as appropriate. And then we would have to find a way to get x by itself by doing first getting the integers with no x's on one side and then getting the x's on the other side by adding and subtracting as appropriate. When we do all of that, we get 7 times x equals negative 27. And we now have a linear equation in the standard form, where 7 is a and 27 is b. So now, we simply divide both sides by 7, and conclude that x is exactly equal to negative 27 over 7. If we are given something that does not involve straightforward distribution but fractions, like this, we can still get it in linear form by remembering how adding and subtracting fractions works. So we would multiply everything by the least common denominator, see that the fractions go away, then distribute the simplified answer, add and subtract like terms as appropriate, and finally get terms of m and constants on different sides. And we can see, fortunately for us, the coefficient of ma here is exactly 1, so we do not have to do any division. We can conclude that m equals negative 7. If we are unsure about this, we can plug in m equals negative 7 directly into the original equation, simplify the fractions using the rules of arithmetic. See, in this case, luckily for us, the fractions exactly simplify to integers without needing least common denominators or anything like that. So now we simply add like terms and get negative 2 equals negative 2, which we know is true. So we conclude that m equals negative 7 is a valid answer. If we have something like this, which involves polynomials greater than terms of x or constants, but instead terms of x squared, terms of x cubed, etc. like this, we would still do the least common denominator method, even if the fractions may be more complicated. We see in this case the least common denominator is 2 times y minus 3 squared. So 2 times y minus 3 in the first fraction cancels out, and y minus 3 squared in the second fraction also cancels out. So now we distribute, and then manipulate the expression so that coefficients of y and constants are on different sides, and then finally divide by the coefficient of y on both sides. We conclude in here y equals 5. If again we are unsure about this, we can plug in y equals 5 in the original equation, and see after we do all the arithmetic, we get 5 quarters equals 5 quarters, which we know to be true. Sometimes, in parts of the simplification, we will get powers of x greater than 1, which will have to cancel out in order for it to become a linear equation, as in this case. We see the least common denominator here is the multiplication of the different denominators. So when we multiply the least common denominator by everything, we see the fractions go away like in the last example, but a new problem appears, in that we have a coefficient of z squared rather than simply a coefficient of z as part of our terms. But fortunately for us, when we distribute out everything, we get 2z squared on either end of the equation, so we can cancel it out by subtracting these two terms. And then we can do the usual process of combining like terms for everything else, and then getting coefficients of z on one side and numbers with no coefficients on the other side, and then dividing both sides by the coefficient of z, and simplify the answer if it is appropriate, which it is here, as we see the numerator and denominator have a common factor of 3, and 3 is the greatest common factor of both of these terms. If we are unsure that this value is correct, we can plug it back in to the original equation, and see the arithmetic here is a lot more messy, but if we are very slow and careful in how we carry out the work, we can see the fractions simplify, and as we get it more and more simpler into its simplest form possible, we can conclude that 17 over 13 equals 17 over 13, which is true. So z equals 17/3 is a valid answer. However, the caveat to fractions, no matter how simple they may look, is that you can never get division by 0 when you plug back in values of x, as this example will demonstrate. We first factor both sides into their simplest form to get the least common denominator, which will be x plus 2 times x plus 3. So when we multiply by this, the fractions go away. And we next distribute on the left hand side, get all the constants and all the x's on either end, and see, even though we did the work properly, x equals -2, which gives us division by 0 on both the left hand side and the right hand side. So we conclude that this has no solution or no specific value for x. Now that we have figured out how to solve linear equations for x, as well as how to simplify more complex expressions into linear equations, we can move on to the basics of quadratic equations next, which are quadratic expressions that are equal to 0 where we solve for exact values of x. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.